13th edition of the video training on robotics inspired science education. In episode 12, we looked at fault tolerance, and under fault tolerance, we considered fault detection and correction. Before we move on to fault avoidance, we want to look at the programming session for fault detection and correction. And if you recall from our previous video, as displayed on your screen, we had a robot that was supposed to follow this black line on a white tile. And our idea was to come up with a reference location that is a light sensor positioned exactly half on the black line and half on the white mat. And in that circumstance, if the light sensor was calibrated, then our expectation was light sensor reading of 50% reflection from the light sensor, since the black portion of the line will absorb exactly half or 50% of the light, and the white portion will reflect exactly 50% of the light. So to detect whether the light sensor is deviating from this reference position, we came up with an error formulation formula, that is an error detection formula, which was, as we see, error being equal to the light sensor reading minus 50. So anytime the light sensor goes above 50, it showed that the light sensor had drifted more into the white than the black. And on the reverse, if it goes below 50, it showed that the light sensor had gone more into the black than the white. So from our error detection formula, we formulated an error correction formula which applied to the motors that control the movement of the robot. That was motors on port A and port D. So if both were moving at a default speed, then depending on what error had occurred, we use a proportion of that error to either increase the speed of one motor and slow down the speed of the other motor, or vice versa. This is possible because the value of error is a vector quantity which can either be a negative figure or a positive figure, and depending on which one comes out, if there is a negative error, then A will end up slowing down and D will end up speeding up. On the reverse, if there is a positive error, then A will end up speeding up and D will end up slowing down. So we are going to look at that in programming. So let's move to our programming session. Here I have a calibrated light sensor on port 1. I picked that, and as we can see from the previous video, our error formulation was light sensor reading minus 50. So I picked the math block under data operations, math block, to perform subtraction. I plugged in light sensor reading at port A minus 50. So the result that comes out of this computation is the computed error value. To keep that value, I pick a variable because the value will be used in the error correction formulation. So I add a variable. Let's call the variable error. I plug the result into that error formula. Then now we have our error formulation, so light sensor reading minus 50. Now we need this error value to do the error correction. So there is a default speed. Because this program is going to be running on the robots, I'm going to put it in a loop, so this will have to be constantly done. At any point in the robot's navigation, it should be calculating the error. Now, to do the error correction, there is a variable that we are adding to store the speed value. So let's take that as the default speed. So assuming we set a default speed of 40, then what it means is that both motor A and D will be speeding at 40 if there is no error. That is, if error is 0, then this computation ends up at 0, and that also ends up at 0. So to do the error correction, there is a motor on port A which would have been driving at a default speed, so I turn it on, which would have been driving at the default speed, so I pick my variable for speed and I read its value. So this should have been the constant speed of motor A if it was supposed to be driving on a straight path. However, from our error correction, we have seen that depending on the error that is occurring, this speed will either have to slow down or speed up. So I'll pick the math block again and say that the speed of motor A will always have to speed up by a fraction of the error value. So as we see, a constant of proportion, that is a proportional gain times the error value. So let us introduce that constant of proportionality. Let me add this as a variable. So Kp, assuming we are using 0.5, that is half of whatever error value is measured, then it means the speed of the motor should always drive at, I pick the error value, I read that value, I multiply that value, so I pick the math block to do multiplication. So the error value should be multiplied by the constant Kp. So I pick Kp, we read its value, number, and multiply the two. So what we have is Kp times error, just like we have here. So Kp times the error value. So we have this, and that is supposed to be added to the default speed. So the result of this has to be added to the speed, and then that goes to control motor A. So constant of proportionality, that's the proportional gain times the error, is multiplied here, and then it is added to the speed value to control motor A, just like we have in our error correction formula. Default speed plus the constant of proportionality, which is the proportional gain times the error. Then motor D is supposed to drive at the default speed, this time minus the same fraction of the error. So I'll do that by saying motor D, motor on port D, I turn it on, and it has to drive at the speed, this time minus, so I plug in, or I connect the speed once again, that is the speed minus the proportional gain times the error, that's the output from here, and that goes to control the speed of motor on port D. So we have implemented our error correction formulation also here from this section. So here we have error correction, and then we have error detection implemented from this side. So this is the error detection, where we subtract 50 from the line sensor reading and store that as error, which is a measure of the error that has occurred. Then afterwards we use that measured error to do error correction by speeding up motor A and slowing down motor D, or speeding up motor D and slowing down motor A by a fraction of that error. So this is an implementation of error correction and detection. It is also the same as what we call the proportional controller. So as we'll be talking about PID controllers, this is a proportional controller. It corrects the error using a portion or a proportion of the error. So this is a proportional controller of the classical PID controllers. Thank you for watching this video. In our next episode, we'll be looking at error avoidance using derivative controllers. So we'll have a proportional and then a derivative. We will be adding the derivative part to the proportional part. So we will add error avoidance to the error detection and correction. So our robot will have both an error detection and correction mechanism as well as an error avoidance mechanism. Join us in our next video. Share, like, and comment. If you have any questions, post them as comments and we will address them. Thank you. Bye-bye.